So today we're going to be given information about a rational function, and we want to come up with the equation of the rational function. And before we actually get into the notes, these aren't on your particular notes today, but you've seen this chart before. I just want to remind you that if a function is bottom heavy, then we have a horizontal asymptote at y equals 0. And if it's top heavy, then we have an oblique asymptote. And then if we have the same degree on the top and the bottom, then we have a horizontal asymptote. Just want to keep those three things in your head here as we go ahead and write these equations. I'm going to not do the sketches here because of time constraints. But when I look at these types of problems, the first thing that I like to do is I like to start with the vertical asymptote. And we're going to be writing y equals, and it's going to be a rational function, so it's going to be written as a fraction. What we can do for the denominator, and not everybody has to do this, but we could subtract 0 from both sides, and we get x minus 0. But do we really need to write minus 0? No. That leaves us with x down there in the denominator. And then when we look here at the horizontal, it says y equals 0. Well, once again, if I flip back to this chart, y equals 0 means that we're going to have a bottom-heavy function. That means that the degree of the bottom is going to be greater than the degree of the top. And since this is x to the first power, I would just put a 1. And it can be any number that you want to put in there, but it needs to be less than the degree of x to the first. So if you take a look here at problem number 2, see if you can do that one on your own very quickly, because I really do need to make sure to get to 8 and 9. All right, and I've got a couple that aren't getting it, so I'll keep going here. Start with the vertical, the VA, vertical asymptote. Let's subtract 5 from both sides. If we subtract 5 from both sides, we get x minus 5, and that value, the vertical asymptote, is coming from the denominator of the function. So we're going to put x minus 5 in here. And once again, we have y equals 0. When our function has a horizontal asymptote of y equals 0, it's a bottom-heavy function. And that means that this degree, which is x to the first power, that needs to be greater than the degree of something in the numerator. And again, 1. And it can be any number, but 1 has a degree of 0. So then that makes this a bottom-heavy function, so we have a horizontal asymptote at y equals 0. Nicole, a little bit better? So if we look at 3, following along the same lines, start with the vertical asymptote. And this time we have 2 of them. But the process is still the same. We can subtract 2 from both sides, and we get x minus 2 as one of our values down here in the denominator. We can also look at x equals negative 4, and it's going to be a tight squeeze here for me, but we can add 4 to both sides, and we get x plus 4 here. And then we have y equals 0, so what could we put up there? Because y equals 0 is just like the previous 2. We can put a 1. You do not need to multiply those out. I'm going to go with best. So if we look at the fourth one here, vertical asymptote, still going to start with the vertical. To figure out what's going to go in the denominator, we're going to subtract 1 from both sides. So we have x minus 1. But this time, what we have is we have y equals 2. Because we have y equals some number, that means that we're going to have the same degree. Because ultimately what's going to happen is we need to end up with y equals a divided by b. That's how we would calculate the value of y equals 2. So if we want to have the same degree up here, then that means that it's going to be x to the first power, because down here in the denominator we have an x to the first power. But to get our ratio here of a over b, we would have to put a number in front of that x, in this case of a 2. And if I digress for a moment here, this would have been the numerator. We would have looked at it and we would have said it's 2x. The denominator is 1x. We would have said same degree, and then we would have said y equals 2, the number in front of the x, divided by 1, the number in front of the x. There's the horizontal asymptote. So let's take a look at number 5 here. And again, very, very similar. Start with the vertical. And when we have the vertical, you can show the work or you don't have to. I hope that you can just convert it in your mind. If we subtract 4 from both sides, we get x minus 4. If we add 3 to both sides, we get the x plus 3. There's our verticals. The verticals are determined by the denominator of our function. But we have a horizontal asymptote of y equals 1. So in this case, what has to happen is we need to have the same degree once again. And this time, on the same degree here, if we look closely at our denominator and we FOILed this out, we would get x times x is x squared. So we need to have a degree of x squared in the numerator. And then it's going to be y equals a divided by b. Remember, it's the 1, and no, you don't have to write the 1. But since the horizontal asymptote says y equals 1, we could write the 1 there just to get it in our heads here. Because it would be the number in front of the x squared, the number in front of the x squared. Casey?
So, do not figure that way, because you just said if you distribute it, it could be x squared.
Right.
We didn't distribute it.
If we go back to 3, I mean, a couple things. Y equals 0. So we just need the degree less than what we've got down here. So we just need a degree that's smaller than x squared. Because we have to have a bottom-heavy function. For real?
Yeah.
Okay. So if we look at number 6, we've got a hole now. We've got removable discontinuity. But still start the way that we've been starting. Let's start with the vertical. So we get y equals, and then our vertical asymptote, very small here, I can subtract 6 from both sides, gives us x minus 6. I always start with the vertical. Well, the next part is that there is a hole in this when x equals 3. So if you think back to removable discontinuity here, what happens is we have removable discontinuity and therefore a hole in our graph when something cancels out. So if I subtracted the 3 from both sides, then we get x minus 3. And then if we have an x minus 3 in the denominator, then we need to have an x minus 3 in the numerator. We need to have it so that it cancels out. Then, lastly, we've got the horizontal asymptote. And what happens is this one says y equals -2. And again, since we have a specific number here that's other than 0, that means that we're going to have the same degree on the top and on the bottom. And if we look down here and we actually FOILed the denominator, we'd have an x squared. So we need to have another x in here so that we have x times x is x squared. So we have an x squared value in the numerator. And then lastly here it says y equals -2. Well, we'd have -2. Just real quick here, even though my time is short, if you look at this function, it would have been -2x squared plus 6x. And then down here, it would have been x squared minus 6x minus 3x minus 9x plus 18 if it was FOILed out. So our horizontal, once again, would be determined because the numerator was -2x squared. The denominator was x squared. And then we would take y equals the number in front of the x squared, which is a -2, and the number in front of the x squared, which is a 1. So as we keep going here, I'm going to jump over to number 8 and then come back to 7. On number 8, we have an oblique. But let's start with the vertical, as always. And can you do the vertical in your head now? X minus 3. There's our vertical. But here's the thing about the horizontal, is we would use synthetic division. And what would happen is, since this is x minus 3 in our denominator, we'd have to put the 3 out there. And we know what our oblique is already. It is 2x minus 3. And remember, we don't need to worry about the remainder there. When we're doing synthetic division, our first step is that we bring this first term down. So since there's a 2 right here, that means that there's a 2 there. Synthetic division is always bring that down. And then we can work backwards. 3 times 2 is 6. It's a positive 6. But what number plus 6 gives us -3? -9. Again, it doesn't matter what we have here in terms of the remainder. So in terms of this, we get 2x squared minus 9x. We do want 2x squared because we need a top-heavy function when we're dealing with oblique. And then over here, it doesn't matter what you put. This number, it doesn't matter. But you need to be careful that you can't factor that and have something cancel out, because we don't have any information there about a whole. Let's look at one more here for my last couple of minutes. Same kind of thing. We want to write our function here. It's going to be y equals the vertical asymptote. X equals -4, then is going to cause us to have x plus 4. Because we have an oblique, that means that we're going to be top heavy in terms of our function. And when we look at our synthetic division, since this is x plus 4, we would have a -4 out here. We know what our function is. Our function, we're left with the number in front of this x, -1 plus 2. Again, we don't care about that remainder right there. But when we're doing synthetic division, this first term we always bring down. So that means that this is going to be -1. And then use that value. -4 times -1 is +4. What value plus 4 gives us 2? -2. So again, just to go over this, we carried down this -1, or we carried it up because we know what the oblique asymptote is. And then, -4 times -1 is +4, and the question, once again, is what number plus 4 will give us a +2? And that's going to be -2. -2 plus 4 is 2. We don't care about the last part of this here. We don't care about this last value here where the remainder is. But what we need to write as our function is a top-heavy function. So we have to have it 1 degree bigger than the denominator. So this is going to be -1x² plus 2 plus some value. And the 5 there that I wrote in can be any number. But the thing that you need to watch out for is if that numerator can be factored, you need to make sure that a factor from the numerator and the denominator don't cancel out. We don't have a whole as a characteristic in this function. So lastly, let's go back up to number 7 here and finish that one. We have a horizontal asymptote, we have a vertical asymptote, and we have a whole when x equals -1. Start with the vertical. And our vertical is going to give us x minus 1 down there in the denominator. But when we look there, the whole, removable discontinuity, we need to deal with that as well. And we can add 1 to both sides to get our x plus 1. So I'll scoop this x minus, whoops, no I won't scoop that x minus 1 over. But let's put that value in the denominator. And the thing is, if we have an x plus 1 in the bottom and we're using that value to get our removable discontinuity, then we need to have an x plus 1 in the top. The canceling is what causes the removable discontinuity, which is also known as a hole on our graph. We also have on here a horizontal asymptote. So we've got a lot of information here, but our horizontal asymptote is y equals 2. And because of that, we need to have the same degree in the top and in the bottom. So we're going to put in another x here because that's going to give us x times x is x², the degree in the top. And then if we FOIL down here, we'd have x times x, x² in the bottom. And we need to have y equals a divided by b turn out to be 2. So this is going to have to be 2x divided by the x minus 1 times the x plus 1.